Hello everyone, and welcome to Calculus class. In this course, we're going to learn about limits, derivatives, and integrals. We're going to begin with a study of limits because in reality, derivatives and integrals are all simply just applications of limits. So the better you understand limits, the better you'll understand calculus. The notes that I'll be teaching from can be found at my webpage, which you can find by just searching for Jed Wilshire, and you can go to, it's usually this top link, and you can click on Calculus, and you can download the Unit 1 notes and follow along at home. I'll be using the Desmos graphing calculator from time to time to help with graphing and making tables of values, and that's at desmos.com, desmos.com, and I'll include a link to these sites in the description for this video. So let's get right to it. This is Unit 1, Limits of Functions. In this lesson, our first lesson, we're going to be approximating a limit with a graph and a table of values. So we're going to use a calculator to complete the table and estimate the limit. We'll draw a sketch of the graph just to kind of document our journey. Okay, so I've got our example problem here, just in a simple paint page so I can draw on it. And I've also got our Desmos graphing calculator here that will help us complete this assignment. Okay, so let's read this together. Use a calculator to complete the table and estimate the limit. This, right off the bat, you see we've got some new notation that we get to discuss. This word here is pronounced limit. And it's just written LIM, and it means the limit as x approaches 1. And so that's how you'll say it. You'll say the limit as x approaches 1 of this function here, square root of x plus 3 minus 2 all over x minus 1. So what is a limit? Well, non-formally, it means what is the value that this function is approaching when x gets really close to 1. So we're going to look and see what value is it. So it makes sense that we should evaluate some values really close to 1. So I've included in our table 0.9, 0.99, 0.999. So we're approaching that x value of 1. I've also included 1.1, 1.01, 1. That should be 0.001. I've also included those as well because we need to check and see what is x approaching when x is less than 1, but coming from what we say from the left, we also need to check and see what is it approaching when x is coming to 1 from the right. So we're going to look and see what it's approaching. I've also included the number 1 as well, so we can see exactly what happens at x equals 1. All right, so I'm going to call the function f of x, which is the square root of x plus 3 minus 2 divided by x minus 1. And there's our graph. Let's take a look at a table of values. So I'll just tell it f of x again, and then if I go to settings, I can click on that, and I got a table. So now I got a table and I've got an equation. You can always change that. All right, so let's type in some different numbers here. We got 0.9, 0.99, 0.999, and we'll just document what we've got here. So we had 0.2516, it looks like. In fact, I think I'll just use the typing tool. Then we got 0.250, looks like 2501, right? 0.250, well, 02 if we round to 4 decimals. All right, and then the next one, 0.25001, if I take it out to even 5. If I leave it at just 4, it's just 0.2500. So from these numbers here approaching 1, but from the 0.9s, as we keep adding more 9s, it appears that this number is getting closer and closer and closer to 0.25. Next, let's look at what happens at 1. Well, you'll notice it's undefined. It's undefined there because that would cause me to divide by 0. If you plug in a 1 for x, it doesn't matter what's on top. The bottom is a 0. If the bottom is 0, it's undefined. Now, let's see what happens as we approach 1 from numbers just a little bit bigger. So at 1.1, I'm at 0.2485, looks like. 0.2485, okay. Then I'm at, let's see here, let's go 1.01, and I get 0.2498, looks like. All right, well, let's try another 001. Okay, well, that one is, put that down a little bit. That was at 1.001, that's 0.24998. Well, if we round that to 4 decimal places, that's basically 0.2500. Now, it's not exactly 0.25. I'm not trying to say that it's exactly it, but I can add more and more zeros before this 1, and it keeps getting closer to that number. Likewise, I could add more and more 9s to the 0.99. It keeps getting closer to that magical 0.25. Well, I'm going to make the assertion that this limit is in fact 0.25. Do you believe it? I mean, that's what a limit is, right? It's what is the function's value getting closer and closer to as our x gets closer and closer, but not exactly equal to 1. Now, if we let x equal 1, you know it's undefined. That wouldn't be good, right? But as it gets really, 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 really close, how close? We call it infinitely close to 1, then we know that it is getting infinitely close to 0.25. Let's take a look at the graph. I'll clear away our table for now. And you can see that that's exactly what's happening. As I approach x equals 1, you'll see the y-coordinate is getting closer and closer and closer to 0.25. It's coming from above 0.25, and it's getting really close to it. And then right when I get to 1, there's a hole. It's undefined. Likewise, if I come towards 1 from the right, from a little bit bigger than 1, you'll notice we're also approaching 0.25, this time from below. So because the value of the function is approaching the same y value, the same function value, as I get close to 1 from below 1 and above 1 on the x's, what we think of as from the left and from the right, we're saying that this limit does exist. So let's go ahead and add that to our little example here. I'm just going to draw a little sketch of what we saw. So this is a 1, and so it's good that you have this in your notes so that you can have a picture of what's happening as well as a table of values. Now don't forget there's a hole right here at 1, right? I don't want to say that there's an actual value there. It's an infinitely small hole, and that's what's going on. Okay, so that's the first example. What I want you to do is to use a graphing calculator or a Desmos. You can get Desmos on a cell phone. It's a free app as well. I want you to go ahead and try your first practice problem. I want you to evaluate this limit. Now, I left off the x values, so you need to pick x values that are close to 0. I need you to pick x values from the left of 0, so just barely negative, and to the right of 0, just barely positive. All right, pause the video, and then we'll go over your answers. Okay, welcome back. Hopefully, you had some success there. Let's take a look. All right, I'm just going to paste this in our paintbrush here. perfect. All right, and I've got my Desmos ready to go when I need it. All right, so this time my function is the sine of 3x over x. Kind of a neat looking graph, right? But let's go straight to our table of values. Click on settings and then click on the table there. And we need to plug in values close to 0. So I'm going to do negative 0.1, negative 0.01, negative 0.001. Oh, what do you think? What does that look like that's getting closer and closer to, right? Looks to me that it is getting closer and closer to 3 from the bottom, right? All right, so that was just documenting our journey here. 2.9552. All right, then we got 2.9996. Then 2.9999. Well, that's basically 3.0, right? That's basically 3.0. I'm going to add just a couple more decimals so you can see that it is not quite 3. But rounded to 4 decimal places even, that would be basically 3. All right, so this is not enough for us to conclude that the limit is 3. Don't get carried away. We got to do both, right? Don't forget, we got to check from both directions. So 0.1, 2.955. 2. A little bit of symmetry here, doesn't it look like? All right, 0.01 and 2.99955. 0.001 and 2.99999 again. We can go ahead and try 0. You know, might as well see what happens. You can see it's undefined though, because once again we have a 0 in a denominator if you plug in 0 for x, and you're not allowed to divide by 0. All right, I think this is conclusive. We could see that it is definitely getting closer and closer to 3 as we choose numbers that get closer to 0 from the positives, and we also got closer and closer to 3 as we chose numbers getting closer to 0 from the negatives. If you look at the graph, I think you can really see how that's happening. Those are all the values from our table, just kind of bunched in right there, and you can see that it's definitely approaching 3, undefined right there at 0, but definitely approaching 3. So I am going to claim that this limit is 3. Never reaches 3. The function never reaches exactly 3. And I also notice that unlike last time where we came from above the number 1/4 and below it, this time where both sides are kind of coming up from the bottom. You're coming up from getting closer and closer to 3 from the bottom. As we come from the left, as we come from the right, we're getting closer and closer to 3 as well from the bottom. And that's totally reasonable. So I'm not going to try and make this sketch perfect here. I just want to, and I'm not anywhere close to making it perfect. I just want to kind of show what's happening here, that we had this hole right here at 3. Okay? And that's what it's all about. That's a limit. Okay, let's do some more practice problems. Okay, on our next one, we're going to be sketching a graph. And I really want to try and do this without a calculator if at all possible, because you're in calculus now. Calculus is all about looking at a function, not knowing what it's going to do, thinking about it, and figure it out. All your other math classes have been a lot of memorizing and things like that. I want you to just start thinking and puzzling out these functions. All right, let's put that in our, I'll go ahead and expand this out. There we go. Okay, so we're going to sketch the graph. X squared minus 1 when x does not equal 2, and 4 when x does equal 2. We call this a piecewise defined function. They're really important in mathematics for many reasons, and they're important in calculus because it allows us to really kind of address some important issues that happen. We're going to find the limit as x approaches 2. So x squared minus 1 has a y-intercept at negative 1. It has x-intercepts at 1 and negative 1. And it's a parabola. If I were to plug in the value of 2 up here, I would get 4 minus 1 is 3. So I'm going to show that by going up and then putting a circle there, okay? Now, a lot of people in the graph piecewise defined functions forget that just because it says, x not equals 2 doesn't mean I stop at x equals 1. I keep going past it. You get infinitely close to that 2. Then, since it's not x less than 2 or x greater than 2, it's just x not equal to 2, I also have this part of the parabola up here as well. Okay, then what is it when x is exactly 2? Well, for some reason in this function, when x is exactly 2, we're at 4. Right there. So let's evaluate the limit. As x approaches 2 from the left, I'm coming right here, and I'm getting closer and closer and closer to what looks like 3. So we're definitely approaching 3 as I come from the left. Okay? Now, as I get closer and closer to 2 from the right, which I'll show with orange, so as we're coming towards this hole at x equals 2 from the right, we're coming down this parabola, and again, I'm getting closer and closer to the value of 3. So I am going to state that the limit of this function as x approaches 2 is 3. The value of the function at x equals 2 is 4. In the previous couple of problems, we saw that the value at the limit was undefined. This time it's defined, but it's a totally different number. And that's fine, because the value of a limit is not dependent on what the value of the function is at that number. It's what the function is going to as x is going to that number. So it doesn't matter that f of 2 is 4. What matters is that as x is getting closer to 2, f is getting closer to 3. And they got to be coming to the same way. They've got to be matching up, going to that same number from the left and the right. You have to check both sides, or else we would say the limit doesn't exist. All right, looks like you've got yourself another practice problem. Try not to use your calculator on this one. I know it's tough, but if you think about it, those are absolute value bars. Remember what they do. If you think about it, I bet you can figure it out. And see if you can evaluate the limit. All right, let's see how you did. Well, I threw you a curveball, which I often do in my practice problems, but that's good for you. So let's see what happens. X minus 2 divided by x minus 2 is just 1 as long as, for numbers that are bigger than 2. So for example, when x equals 3, 3 minus 2 is 1, 3 minus 2 is 1, 1 divided by 1 is 1. When x is 4, you would get 4 minus 2 is 2, divided by 4 minus 2 is 2. 2 divided by 2 is 1. So everywhere over here, when x is 3, 4, 5, etc., it's always going to be the value of 1. Now, when x is equal to 2, though, you would get divide by 0. So that's not going to happen. So I'm going to show that with an open circle. And and it's just going to be going off to the right forever. All right. What about when x is less than 2, though? Well, that's the thing with these absolute value bars. If it wasn't for the absolute value bars, it'd be 1 again. But because x minus 2 is a negative value for values of x less than 2, we'd be dividing a positive number by a negative number. So for example, if x equals 1, you'd have 1 minus 2 on top in absolute value bars. Well, that's negative 1, but the absolute value of negative 1 is positive 1. But we divide that by a negative 1. So we again have this open circle here, but this time it's going flat down here. So let's evaluate this limit. As I approach from the right-hand side, as I approach 2, remember we're approaching this 2 value on x. As I approach 2, it seems like this branch is going towards 1. But when I approach 2 from the bottom, this branch is approaching negative 1. And remember what we said, they have to match. You have to come from one side and the other and to match. They could both be coming from the bottom to match or from the top or different directions, but these don't line up. So you probably got a little confused with that, but if you remember I said it does not exist. So and that's what we say here. We'll simply say that the limit does not exist. In fact, it's so common, you'll see people simply write D in E, which is fine for me. Does not exist. Why does it not exist? Because they don't meet. They're not approaching the same y value from the left and from the right. And you need to be able to justify that. You cannot say the limit doesn't exist because the value doesn't exist when x equals 2. Yeah, the value is undefined when x is 2. I get that. But that has nothing to do with whether or not the limit exists. The reason why the limit doesn't exist is because you're approaching a different y value as you come at 2 from the left than you do as you come at it from the right. All right, let's see what's next for us. Okay, we've got a graph and we're going to evaluate some limits. So let me pull this over to my paintbrush. Looks like I didn't get quite all of them. We'll come back and get more later. Okay, so we're going to use the graph of f shown on the right to determine the indicated value. F of 0. Okay, well here's f. That's this dark line. These are asymptotes here, I think. Well, yeah, those are just asymptotes. So that's not actually part of the graph. They should, maybe they should be dotted lines. I'm not sure. Okay. So when x equals 0, this is a hole, but down here you see it's filled in. So the answer to that, I'll use blue. The answer to f of 0 is negative 4. Okay. What about f of 1? Well, f of 1, all we have is this hole. It's not filled in anywhere else, at least nowhere we can see. So what we're going to say is that value is undefined. And it's not a super big deal, but I try and, I mix them up too, but I try and keep this straight. A function value can be defined or undefined. A limit can exist or not exist. So existence for a limit, being defined for a function value. Okay, here comes our limit. The limit as x approaches 0. Okay, well, as x approaches 0 on the left, we're coming, I'll use yellow here. We're coming towards, I'm going to say, something like 0.75 maybe. Now, from the right, we're approaching, it looks like as x goes to 0, we're approaching negative 4. But those are not the same number. So because they are not the same number, we have to say the limit does not exist. So I think that's kind of interesting that we had a function value at 0. The function was defined at 0, but the limit was not. And that's totally acceptable. That can happen. All right, let's take a look at the limit as x approaches 1. So as x approaches 1, from the left, I appear to be going towards negative 1. And from the right, I'm also going towards negative 1. So because the function is approaching the same y value as I travel along its curve going towards the x-coordinate of 1. As I travel from the left of 1, I am approaching the same y value as when I travel from the right of 1. So I am going to conclude that this limit does exist, and it's in fact -1. So kind of the exact opposite. The function was undefined, but the limit did exist. All right, let's see. There's some more down there? Or I'll just go grab them from the page again. Oh, we got quite a few more. No way. Okay, I think I can just fit those right here. No longer need that guy. There we go. Okay, so the limit as x approaches -3. Okay, I don't think we've seen one of these yet. This is an asymptote. As x approaches -3 from the left, we're going up and up and up and up to positive infinity. The y is going up to infinity. As I approach -3 from the right, we're going down the negative infinity. So because they're not going to the same value, we have to say it does not exist. Absolutely does not exist. All right, what about the limit as x approaches 5? All right, well, this is a very different situation. As I approach 5, riding along this curve from the left of 5, I'm going up to positive infinity. As I approach 5 from the right, I am also going up to positive infinity. So we can say that this limit does exist. It equals positive infinity. Okay, there's actually a little bit of debate there. If we define that the limit has to equal a real number, well, infinity is not a real number. So you might also see the answer that this limit does not exist. So in fact, both of these answers are appropriate. It just depends on what you're using it for. So there is definitely times where the fact that it equals positive infinity, there's definitely a time where that's going to be an important answer. Other time, you just want to know whether or not it's a real number, and so does not exist is more appropriate. I usually list both because I like to have both pieces of information, or sometimes I'll put just infinity. But there's no debate that the limit as x approaches -3 does not exist, because that wasn't going to the same infinity. Okay, the limit as x approaches -2. Okay, I don't have any dots or anything there. I just want to make this clear. I don't have to have like a dot or anything special happening. I could take a limit at any of these x values anywhere. So the limit as I approach -2 from the right appears to be 0. As I approach -2 from the left, it's also appearing to be 0. So in that case, f of -2 is 0. The limit as x approaches -2 is also 0. So no funny business going on. The limit and the function both agree there. All right, I think you have one more practice problem to do. So go ahead and give this one a shot, and we'll come back and talk about it in just a second. Pause the video and do it. All right, welcome back. I hope you didn't find this one too bad. Let's take a look and see what we can figure out. F of 1. Well, I think we see where that is. That appears from the graph to be 1. Right? Using just the up and over, go up to the curve at x equals 1, and then take it over to the y-axis to get y equals 1. The limit as x approaches 1. The limit as x approaches 1. As I approach 1 from the left, I'm going to positive 1. As I approach 1 from the right, I'm also going to positive 1. So the limit is also the number 1. All right, let's do the limit as x approaches 2. The limit as x approaches 2. So if I come from the left, I'm going to the y value 4. But as I come towards 2 from the right, I'm going to a y value of 1. So this does not exist. What about f of 2? Does that exist? Yeah, that one does. It's the colored in circle. That's at 4. How about the limit as x approaches 4? The limit as x approaches 4, from the left, it appears to be a 1. As I travel the curve towards x equals 4 from the right, It also appears to be a 1, so we're going to conclude that the limit is 1. F of 4, that's undefined. Okay, well, that's it for your first calculus lesson. There'll be homeworks that you can link to on the same webpage that you got my notes at, and so be sure to download those and do the homeworks for lesson 1. You've got to practice every day so that you get better and understand it. All right, I'll see you next time.